All right, guys. I know you guys loved the last uh, week's presentation by Puya. Puya was the presenter. We have another excellent colleague here, um, Dr. Sanjib Soor. You know, if I had to say in one kind of sentence, he got a very prestigious NSF Career Award. So when a faculty goes, when there's a new faculty, uh, that kind of, if you get that award, that separates from uh, the whole group, and it's a matter of pride for the departments when the faculty won this award, and he has other awards also. He's in an area which I don't understand too well, but into both networking aspects and the particular type of millimeter wave, and he's also in the sensors and Internet of Things. I think so. As you collect data of various kinds and to the network, get it, and then he uses machine learning and other techniques to analyze the data, and we'll discuss the applications of that. I just was talking to him about his another grant which has very cool application in mining, and we will talk about some of those behind us. So thank you, Sajid, for joining us.
All right, thanks, Amit, for that kind introduction. And hello, everyone. I think some of you already know me. I am Sanjib Soor. Just a little background about myself. I'm an associate professor in the computer science and engineering department. I got my PhD from University of Wisconsin, Madison, about 6 years back. My research area is in next generation networks, think 5G, beyond 5G towards 6G, machine learning, autonomous system, and their applications in healthcare sensing. Most of my research are funded through National Science Foundation and Department of Defense, and we recently had a grant also from National Institute of Health related to this healthcare sensor. So with that, let's get started with today's talk. We have two objectives for this talk. The first one is I'd like to provide you a very high-level overview. There's nothing coming here, but I don't know what is that. But it's okay. I think we'll manage. I'd like to provide you sort of high-level overview of this 5G millimeter wave-based signal processing and customized machine learning algorithms that can be used for what we call contactless sensing. And then I'm going to show you some results, some preliminary evidence on using our sensor and compare them with other traditional routine approach like cameras or smartwatches in monitoring, contactless monitoring of stroke patients, real stroke patients, in understanding their gait speed, limb weakness, and bed transition times. But let's take a step back and discuss why are we interested about 5G today. The application of 5G goes beyond high-speed connectivity, that's what you might be all familiar with. You may get advertisement for Verizon, AT&T saying 5G can achieve like gigabit per second speed, but it goes beyond that. There are applications in transportation, physical security, and healthcare sensing where 5G, we believe, could be to provide better solutions. And one of the research goals in our lab is to bring this cutting-edge imaging, sensing, and healthcare application to the masses using this already existing technologies. And in the purpose of today's talk, I'm going to focus on this healthcare sensing aspects of millimeter wave that we are conducting research in our group. So back in 2020, when 5G started like popping up here and there, we had about barely 190 million subscribers. And within just 4 years, that grew to 10 times, almost 1.9 billion subscribers today, a 10x increase in just 4 years. And this growth is likely going to continue, driven by this massive demand of wireless and connected things today. One of the new technology of 5G is this millimeter wave technology. A tiny antenna that goes in your smartphone, goes to cellular base station, that can achieve a very high throughput on the order of gigabit per second to tens of gigabit per second using very high frequency signal that we call millimeter wave signal. But not just high-speed connectivity. Millimeter wave has been shown to have applications in, apart from high-speed connectivity, an application in remote sensing, like weather forecasting, weather monitoring, in achieving covert communication, has been used by US military, and also is used by TSA, security scanner, when you pass through airport. They can actually see through your clothes and detect if someone is carrying contraband objects like hidden guns or knives. They use this millimeter wave technology. So we imagine that given this, 5G will become more proliferated in coming days. This kind of millimeter wave technologies, the sensors will become cheaper and can potentially apply, enable applications far beyond this high-speed connectivity. So rather than me telling what is possible, let me show you a couple of demonstrations on using this millimeter wave technology in our lab. Unfortunately, you cannot see that title. I don't know why it's blocking, but this is the objective of this demo is to build a contactless sensor that can monitor someone's vital sign, their heart rate and breathing rate, without having to put any sensor on their body. So in this picture, what you're going to see is this millimeter wave device, a custom millimeter wave device that we have designed, a subject sitting around 1.5 meters away from the device. And we're also going to use a smartwatch to compare how millimeter wave picks up its vital sign and compare them with a real FDA-approved smartwatch. So when the video plays, you're going to see some that at some point in time, I'm going to ask, by the way, this is one of my graduate students, Juan. I'm going to ask him to open or take off his smartwatch, and then show you how millimeter wave can still estimate his vital signs, specifically the heart rate and breathing rate. So when the program starts, what it's currently plotting is this black line, this heart rate and breathing rate directly measured from the smartwatch. And when I turn on the millimeter wave device, this red line measures his heart rate and breathing rate based on the contactless sensor, the sensor that is placed about 1.5 meters away from his body. We actually have a very good correlation between the smartwatch and the contactless sensor. And the idea is this devices can transmit signal towards someone's body and get a reflection back. By analyzing those reflections, by tiny change caused by the heartbeat and its breathing pattern, we can pick up the heart rate and vital sign. At this point, I asked him to open this smartwatch, and you'll see the smartwatch measurement goes down, but millimeter wave keeps going, and we can still pick up his vital sign without having to use the smartwatch. Go ahead.
Are there any significant interferences that would?
Right now, in this demo, at least there was none, because the frequency that we are using is far beyond what is available in traditional Wi-Fi. This actually uses a frequency on the order of 70 gigahertz. Your traditional Wi-Fi works at 2.4 to 5 gigahertz. Of course, when things will get deployed, like more millimeter wave will get deployed, we might have interference. But the advantage of this device is you can steer your energy spatially, so you can focus on one direction at a time and pick up the vital sign, and also can track the user as, let's say, he's walking in his home without having to put any sensor on his body. Right? So that is one example of what millimeter wave can do, contactless vital sign. Here's another demo that I want to show. In this demonstration, we'd like to use the same millimeter wave device, but not just pick up the vital sign, but rather use it to understand the activity of the user in front of the device. Like, for example, if some user is doing some specific exercises, can we classify that exercise and how long he is doing and what kind of exercise he's doing without actually having to use any camera or having to put any smartwatch on his body? So here in this example, we'll build a kind of like a front interface where you can see that the subject walks inside, we detected there is a human present, and the person is currently standing, and we are able to accurately classify that standing behavior. And this output is not using any camera, but rather using the signal that's reflected from that person's body. And you can see also some of the reflection that we get from his body. At some point in time, hopefully he will start doing something. Yeah. So I asked him, can you start walking in front of the device? And he walks, and now, but based on the pattern of this change in the signal, we're able to pick up and classify his type of activity is walking. Also, apart from walking, we sort of ask him, can you do different kinds of exercise, like do lunges, do squat? And hopefully we'll be able to pick up that. So at this point, he's sort of doing this lunges. And based on the change in the signal pattern that is reflected out of his body, we build a classification algorithm that tracks the activity and classify the type and the duration. Use an example of arms up and down and squat. Squat was the hardest exercise to do, not just to do that, but also to classify. Question?
Does it work through the obstacles?
Very good question. Depends on the obstacle type. If you have a very thick concrete wall, the signals won't penetrate and will not get a reflection back. But if you have a dry wall, like typically what we have, dry wall works fine. You still get a signal reflection through the dry wall and you get a penetration back. Good question.
Kind of there's no maybe privacy.
That's always a challenge with any new technology. But we believe, like, because we don't capture like images, right? Someone is doing something, there is no RGB or color information, there is no facial information. We believe it's more like a little more private than using a camera to do that classification. Finally, I want to show you another demonstration of monitoring sleep in terms of when the person went in at the bed, what kind of position she's sleeping in, and then also pick up the vital signs, the heart rate and breathing rate under the blanket without having to put any sensor on the body. So we had this millimeter device sort of in front of this bed. This is one of the bed in our lab. And when the demo runs, initially the bed is empty. We classify the bed is empty. As we walked inside, we detect that there is a human presence in the scene. And now, not just a human presence, but also we are able to classify that she is sleeping in a supine position. Supine means sleeping on the back, right? And the interesting thing is it still works, even if cameras cannot detect anything, because she's under the blanket. And of course, during actual sleep, you will have a dark conditions, so cameras won't work. And not just that, we are able to also pick up her vital sign, the heart rate and breathing rate, without having to put any sensor on the body. And here also, like at some point in time, she switched her position from supine to left and then right, and we are able to accurately classify them.
So the whole intellectual property is in the sensor you design that others don't have, or that is in the other things?
The sensor is open source, where you can buy it right now, right? But the core intellectual property is what I'm going to talk next, is this coming up with a model that converts the signal reflection pattern to what's happening in a real human body, right? So that's perfect segue for my next set of slides of how it is even possible to pick up what someone is doing in terms of activity once someone enters the bed, exits the bed, what position she slept in. How is it even possible just by looking at wireless signal, the wireless signal that you use to connect to the internet? So imagine a subject that is in front of our contactless sensor. We sort of illuminate the subject by transmitting signals towards the subject. And each part of this body is going to reflect the signal back. Now, the interesting part here is some part of the body is going to reflect the signal early because they are closer to the sensor, and some part will reflect the signal late because they are farther away. At the end of the day, what you're going to get is this kind of one-dimensional signal where you will be able to sort of track the reflection patterns at different parts of the body. And you can separate them in time. But unfortunately, the subject is in three-dimensional, but the signal that we get from one sensor, one antenna, is a one-dimensional signal. So how can we map it to a three-dimensional space? Well, for that reason, we can actually transmit from multiple sensors simultaneously. And the cool thing is This sensor can be placed very close by so that your device can be very small, since we have a very high frequency. And all these reflections is going to be captured from where we can create something called a volumetric reflection. So all parts of the subject's body reflects back, and we can track them over range and create this three-dimensional volumetric reflections. Now, this 3D volumetric reflection then goes through a series of signal processing steps that involves Fourier transform, inverse Fourier transform in 3 dimensions. And then at the end of the day, we sort of build a customized machine learning engine that converts this 3-dimensional volumetric information to a human perceptible, human-like body structure. And the cool thing here is you don't need any camera or you don't need any sensor to be placed on the subject's body, but we can get a comparable body structure of the subject, and we can repeat this process hundreds of times in 1 second, so we can track the subject and understand the motion of different limbs and positions within the room. And that's the crux of why those demos that I was showing, detecting different exercise types, detecting what position someone's sleeping in, detecting at what position someone entered the bed or exited the bed is possible. Not too much to, I'm not going to deep dive too much on this machine learning engine, but at a high level, you can think about it's a combination of a conditional generative adversarial network, CGAN, and transformer, where we are able to convert from a signal space to a human biomechanics space without using any cameras or any sensor on the body. In the interest of this talk, I'm going to, and in the interest of time, I'm going to focus on how we are leveraging this sort of camera-free and contactless approach in monitoring stroke patients for their rehabilitation. Why do we want to monitor stroke patients? Well, more than 90% of acute stroke patients suffers from impaired coordination. They either their gait pattern is different, the way they walk, they may have a semi-paralyzed, their limb may have weaknesses. And post-stroke, like after they get discharged from the hospital, you want to monitor how well they are recovering, either at their home or bring them in the clinic by measuring those gait speed, patterns, and limb weaknesses. These are traditionally measured in clinics, but of course that costs time and money, because to bring patients, someone may not be able to travel to the clinic. It costs money both to the insurers and insurance agents. And South Carolina is sort of right at the buckle of what we call stroke belt. So with highest, some of the highest stroke rates in the US with rising costs for rehabilitation. So we want to see how well our sensor can be leveraged in contactless and camera-free monitoring of the stroke patient. So potentially we can do this rehabilitation at their home without having to bring the patient at clinic or having to put any sensor on the body. Now, why do you want to do a contactless and camera-free monitoring? Well, first is compared to a smartwatch, it enables sort of more continuous frequent assessments of their gait speed and motor function. Typically, older folks, they don't want to wear a smartwatch at their home. Sometimes they forget to wear it, and sometimes they even forget to recharge it. Here, in this case, if you have a contactless solution, then there is no need for patient to be involved in this monitoring process. You can do it remotely in a private manner without having to have an active participation from the patient. The second advantage, of course, is there is no camera involved. If we use our camera-free solution using this high-frequency technique, then it actually ensures privacy. Nobody wants cameras recording at their home, in their bedroom, in their living room, in kitchen, in the bathroom, right? Versus if you have a contactless solution that just purely uses wireless signal, you ensure privacy, patient's privacy and dignity. And finally, we believe that can potentially reduce costs and clinicians' efforts by automatic evaluation, potentially at their home. So to this end, we have 3 aims in terms of contactless monitoring of stroke patients. How accurately can we measure their walking speed, gait speed, using our sensor? How accurately can we understand their limb motion, the weaknesses, and what kind of motion they have? And how accurately we can identify their bed transitions plan. Like when they enter the bed, when they exit the bed, because that correlates with the likelihood of falling down when coming out of the bed. Right? I don't know how much time I will have to go through all the aims, but I'd still like to touch upon some of the results. But before we can run any tests for actual patients, we have to really bring them in a lab, and for that we build this contactless observatory. It's actually in Horizon 1 building. So this is actually an all-perceiving chamber. It has many cameras mounted in their ceiling, and those cameras will be used to extract the ground truth, the true motion of a patient inside the room, and then we are going to use one of our contactless sensors to compare how well we are doing. So in last summer, between March to June, we brought 10 stroke patients from local Prisma Health, and we also recruited 10 control subjects, and we collaborated with Dr. Shovich, and a vascular neurologist at Prisma Health, and the patients were from his clinic, and ran experiments and compared how we are performing in comparison with the camera-based systems, which can do a precise motion estimation. So when a patient comes inside our lab, we run a couple of tests. The first one is we obtain informed consent, and then we run a sitting test where we go through a standard NIH stroke scale process. This process involves a healthcare provider asking patients to do some stuff, like, can you raise your arm and hold it for 10 seconds, right? If a patient has a semi-paralysis, he may not be able to do it, and the healthcare provider actually will score it. And that score will get summed for different activities, like, can you move your left and hold it for 5 seconds? And those scores will get added together, and then at the end of the day, a healthcare provider can assess what is the severity of stroke and how well someone is recovering. So we conducted that test, and then we also conducted a walking test in which we asked the patient, can you walk from this point to that? We measured their gait speed using a clinically valid method, and also employed our contactless approach in understanding the performance. And finally, we asked the patient, can you go inside the bed, observe how long they are taking, to enter the bed, exit the bed, what kind of position they slept in, and compare how the performance of the camera-based systems and our contactless systems. Let me quickly go through some of the results that we got. First is I want to focus on the gait speed. Understanding someone's walking speed using camera-based approach, clinically valid approach versus our contactless sensor. Before showing the result, first I want to show you some visual illustration of how does the walking pattern look like from our contactless sensor when you have a healthy patient versus a stroke patient. A healthy subject, and a stroke patient. So the top plot is going to show you a healthy individual, and we're going to track its left and right foot as he walks. And the plot here shows their walking pattern. Okay. And as you can see that when the subject walks, he has a quite high walking speed with a long stride and symmetrical gait pattern, which is what we expect from a healthy individual. What happens if there is a patient? Well, we track the left and right feet and then try to see how the gait pattern looks like. And as you can quickly imagine, the patient had a left side semi-paralyzed. So while he walks, he actually makes a wide swing of its left feet to try to balance himself while he walks, creating this asymmetric gait patterns. And of course, he has a very, very slow speed. So at least from these examples, you can clearly distinguish a stroke patients from a healthy individuals using our contactless method. But can we estimate, how accurately can we estimate the walking speed, which is one of the key indicators how well someone is recovering after stroke? So to estimate the walking speed, what we do is using our contactless sensors, we transmit the signals at a very high rate, 100 millisecond, at a 50 millisecond interval. And then for each of the instance, we track their body structure using our algorithm that I mentioned, and then track the left and right foot and estimate how far he walked and the time it took. And the speed is going to be distance over time. So first, it requires us to locate the subject in the space, again, not using camera, but just using the signal. For that, we estimate what we call range angle heat map. think about range angle heat map, it's sort of like a bird's eye view of the entire environment. And as the subject walks, we get a probability map of where the subject could be located. I mean, it looks something like this. But here's one challenge. The subject could be anywhere because this strong color represent the possibility the subject is either here or here or here. So how can we actually accurately track a subject? Well, we can track it by filtering out the dynamism and the static nature of this heat map. Essentially, apply a background filter where we can take multiple frames over time and see what reflections did not change, which correspond to the reflection coming from walls, ceiling, or floors or chairs, and then identify what is the dynamic part of that reflection, that bird's eye view. And then the one that gives you the strongest one has a highest probability of the subject being in that location. We can track them, cluster them, and then locate the subject on that space. But how do we estimate the speed from there once we have located? Well, we can use a sliding window as the person walks. We use this a long sliding window with a long duration to track the body location over space, and a short time window to estimate the start and end time of his walking path. And then once we have found the distance he walked and the total time it took, the speed is nothing but distance over time. So with that, how does it look like for a gauge speed estimation for those patients? Well, in this plot, I'm going to show you some results. The x-axis is going to show clinically valid gauge speed for the subjects, and the y-axis shows how our contactless sensor works. Any line that falls on this diagonal line, any points that falls on this diagonal line would be considered a perfect result, and our sensor is pretty close. Among those 10 stroke subjects we tested, we got a correlation of 0.99, which is almost perfect match. And in fact, some of the highest error we got for some patient was very low. So this is one of the examples of where we got the highest error, where the clinically valid method shows the patient had a walking speed of 0.51 meter per second, and we predicted the patient has about 6.6 meter per second. On average, our error was close to 0.03 meter per second compared to a clinically valid method with a standard deviation of 0.02, which means that our contactless sensors can detect those minimal clinically important difference in the gauge speed and identify how well a patient recovers. For control subjects, the errors were a little higher because one reason we can guess is the control subject itself walked with a higher speed, and our sensor sampling rate might have to be improved to track that fast walking speed. But at the end of the day, the mean error was sort of like 0.14 meter per second for 10 control subjects that we tried with standard deviation of 0.1 meter per second. So I'm going to skip the explanation of why we had this higher error. I'll just briefly mention it. In summary, the 10 stroke patient we tried, we had a mean error in their estimating gauge speed using our contactless method was 0.03 meter per second and standard deviation of 0.02 meter per second, which indicates that sensor is able to detect minimal clinically important differences. And for control, the error was higher because of their higher walking speed. But where it matters, our sensor works well. Okay. Now this is a preliminary study. We want to actually expand it to next recruit like 100 stroke patient. Recruiting patient is always challenging. Imagine you have to schedule the time. You want to bring them. Some patients are not able to walk properly. You need to schedule wheelchairs for them. So it was a fun and exciting preliminary study with 10 stroke patients, but we want to expand it and then refine our technique as we go forward. In terms of walking and the pattern of walking, I also wanted to show you some results on this standard tests of stroke patients, what we call Fugl-Meyer test. In this test, what happens, a healthcare provider asks patients to execute some actions. So for example, can you lift your arm and slide it over your shin? Lift your right arm and slide it over left shin, or lift your left arm and slide it over right shin. how does it help? Well, it actually indicates whether the person can perceive the instruction, whether the person has enough strength on their limb to actually move up and down, and so on. So there are many instructions like this where the healthcare provider will ask the patient to do some postures or gestures using their hand too, in understanding upper extremity and lower extremity weaknesses. So in our experiment, we wanted to test how accurately we can identify those actions using contactless sensors, and also how accurately can we measure the duration of those actions. So let me show you one example of a patient doing one certain action of leg up and down, and this is what camera picks up. So in this case, the patient was asked, can you move your left leg up and down 2 times, and then right leg up and down 2 times. Pretty straightforward. Any computer vision-based techniques will be able to potentially pick up that activity. But our approach is, can we do it using a contactless approach? The advantage is, next time you can actually deploy it in someone's home, and you don't have to bring the patient in the clinic to estimate how well they are doing. You can actually deploy the contactless sensor and pick up those signatures and then score them automatically to estimate how well they are rehabilitating at their home. So for this kind of action, what our sensor sees, well, this is the kind of observation we got. So the top plot is going to be for the left leg actions, the middle is for the right leg actions, and the bottom one is a combined left and right leg. So let me elaborate and expand on this scenarios. The first is, these actions correspond to the patient walking, and we did the gait speed estimation. And then we asked them, can you move your left feet up and down 2 times? And that actually shows up when we track the left feet position using that body structure estimation that we did. Okay. And then followed by that, right leg up and down, reverse right leg, and reverse left leg. And then we asked, like, can you put your left leg on the right shin and put your right leg on the left shin, and so on. The bottom line here is, our sensor is sensitive enough that it can actually pick up those minute actions done by the patients. In this case, the lower extremity, the right and left leg, without actually having to introduce any cameras. Interestingly, we can also pick up if the patient is doing something wrong. So we ask the patient, can you do it 5 times? Can you move your right leg and like move up and down 5 times? And actually she did it 6 times. That actually also shows up in our measurement. To understand this unique signature, we build a classification, a simple decision tree model, where we sort of detect the peaks based on a threshold distance, the distance, the peak distance of this actually moving the leg on the z-axis, and then based on that, classify where the values are within a certain threshold, and then find out the duration for that action. And we repeated the test and built different decision model for 10 different actions. The first 6 correspond to all lower extremity actions, like left leg down and forward, right leg down and backward, left leg on shin, then right leg on shin, and then so on. And the other 4 actions where all the actions correspond to upper extremity, right? Answering telephone with your right hand. If someone has a semi-paralyzed in their right hand, they won't be potentially able to do it properly, and that actually will show up in our sensor. So here's one result that I want to show. There's actually, the bar plot shows the difference in the duration of those actions picked up by our contactless sensor in comparison with the camera-based approach. And on average, we had a lower extremity error less than 1 second, and upper extremity error close to 2 seconds, which means our sensor is also sensitive enough not just to classify which actions the patient did, but also identify the duration, both of which are necessary to score the patient's actions correctly. I want to also show you some results, quick results on conducting the NIHS steps, where similar to Fugl-Meyer actions, this was more of a patient sitting in front of a healthcare provider, and they are conducting experiment by asking some questions, and also like and again understanding the limb weaknesses. So I'm going to focus mostly on this limb weaknesses part, and then show you how accurately we can identify those duration. So here's an example of one of our control subject. We asked them, can you raise your arm and hold it for 10 seconds? For a control subject, this was pretty straightforward, and this is what our sensor picks up. Both for a right and left arm, we can track it, and you can see that where the arm was raised, and then she was able to keep it for actually more than 10 seconds. Compare that with what happens with the first patient. How does the signature change if we give them the same instruction? This is how it looks like. What's the difference? Well, you can see that his right arm was okay. He was able to hold it and keep it stable for close to 10 seconds, but he had a semi-paralysis in their left hand. So he was actually not able to lift it, first of all, and then was actually trying to use his right arm to lift the left arm. So actually create the motion in both the right and left. And our sensors can pick up that motion. A little more illustration of this raised arm in sequence. Here's one example of sequential estimation of the pattern that we got. So the patient, the subject is sitting in a normal posture. We track their arm positions, the left and right arm positions. At this point, the patient actually lifted their right arm, and you can see there's a signature here. Here's a distance change in the z-axis, no change in the right arm, and then followed by change in the left arm, and then followed by right hand. So the idea is here we don't need a camera to detect all those minute signatures. We can just use our contactless sensors to classify and then track the actions. And here's a set of actions that we studied in our preliminary results, like raise arm, both left and right. There's another action like, can you take your arm and touch your nose? This very act of coordination actually detects if the patient has hand-eye coordinations and also has some deficiency or not. And overall, the result shows that out of this 10 patients, we're able to not only classify all the actions accurately, but the upper extremity actions had a mean error of about 2.5 seconds compared to a traditional depth camera-based approach, which can give you an accurate skeleton measurement. You can track them well. And lower extremity error was a little higher, about 8-second difference. And we believe that the high error is caused by the sensor is more focused on the upper part of the body. So if you put a sensor on the lower side of the body, you may be able to improve that. Finally, I want to show you some results of this action of asking the patients, can you enter the bed, exit the bed? And that has an application, not just understanding how long a patient stays in the bed, but also preventing their fall. So for example, if the patient has a high risk of fall, and when they are about to come out of the bed, if we can detect that, we can potentially create an alarm or trigger an alarm and give them to the caregiver without actually installing any camera or putting any sensor on their body. So that's kind of the motivation behind this. And I want to show you some of the results of this bed entry and exit detection and compare that result with the camera-based systems. So here's an example of our data collection setup where we had this tripod looking at this typical regular queen size bed. In a home setting, you may not need tripod. You can actually mount it in a wall and leave it there. And the contactless sensor was placed here. And we also had a Z depth camera with RGB information looking at the camera information. We can precisely identify the true entry and exit points in the bed. Right? So let me show you some illustration of how it looks like from this when a subject walks and go inside the bed and compared to what our sensor picks up. So here's an example of, by the way, this is not a stroke patient. This is a control subject that walks from a specified position and enter the bed. And this is what our sensor picks up. So this is, you can think about this is the bed and the sensor is placed here, which is looking at this angle. And this is the bird's eye view that we are able to estimate using the sensor reflection. So we actually can map the bed well and then identify the patient when they enter and exit. Create sort of like a virtual geofencing within the environment to detect the motion of the subject. Based on that, we estimated the duration of both patient and control, the duration of this act of entering the bed and exiting the bed. Let me show you some of the results. Here's an x-axis that shows what would be the duration the subjects took based on a camera-based input and what our sensor predicted. And the correlation for a control subject was moderate, not very high, but at the end of the day, the mean error in identifying that entry duration for control subject was less than 1 second, right? Control subject by definition has a high walking speed so that they will take shorter duration to walk inside the bed, right? That's given. So even if we have a moderate correlation with the camera-based systems, the mean error was less than 1 second, which is fair. What happens if we have real patients, real stroke patient trying to enter the bed? This is what the result looks like. For real patients, the entry duration could be anywhere from 0 to 25 seconds. And our contactless sensor had also a very high correlation. In fact, the average error was still less than 1 second, even if the patient took a longer time to enter the bed. What about the exit time? This is an example of results for control subjects. Again, the correlation was not that high, but given that the control subject took shorter duration to exit and come out of the bed, we can still detect that, and the average error was still less than 1 second compared to our camera-based systems. Versus if we had a real patient, we asked them, can you come out of the bed now? The real patient actually took anywhere from 0 to 1.5 minutes, or even like about 2 minutes to come out of the bed. So, and in comparison with the camera-based exit time and our contactless sensor, we have a very high correlation, and the average error was about less than 3 seconds. Now, some of the patients actually took way more time in exiting the bed. So, for example, here, if you look at this particular data point, patient 2 took about 83 seconds, almost close to 1.5 minutes to come out of the bed. And why is that? Because she actually needed help. Because a lot of the patients, they need help from their caregiver to come out of the bed. But even in the presence of multiple subjects, we are able to accurately detect when the person is actually exiting the bed and precisely identify that duration. So in other words, that patient, even it took like about 80 seconds, the camera-based systems said it took 80 seconds. Our contactless sensor estimated it took about 83 seconds for her to come out of the bed. On average, the error was less than 2 seconds in terms of identifying the exit time, which means that potentially we can use this contactless sensor in identifying the fall risk of a patient and this identifying very action of coming out of the bed. In fact, we are currently collaborating with another emergency medicine director at Prisma Health and putting this contactless sensor in the hospital room in trying to compare how well our sensor will perform in typical nurse call. Nurse call is a standard mechanism in which nurses will get alarm when a patient is about to leave their bed. And they have this issue of alarm fatigue because those alarm systems might get triggered for various reasons, even if the patient has a small movement. We believe our contactless sensor, because we have this 3D mapping on the environment and created geofencing, could provide a better alarm, reduce the false positives, and also reduce the alarm fatigueness. And we want to test it out with initially 20 patients that we are deploying in their rooms. In summary, for this bed transition time detection, out of the 10 patients that we tried, the entry and exit time, both of them performed very close to our camera-based systems. Entry time average error was less than 1 second, and exit time average was less than 2 seconds. And it works very well with the control patients as well. So coming back to our original question, how accurately can we estimate the gait speed of the patients? Out of the 10 stroke patients we tried with the preliminary study, we had a mean error of less than 0.03 meter per second, which is quite accurate in terms of detecting minimal clinically important differences. For Fuggelmeyer and understanding limb motions and limb weaknesses, the upper and lower extremity error were less than 1 second and less than close to 2 seconds. For NIHSS, the NIH stroke scale, the lower extremity error was higher because we did not potentially had sensors picking up those lower extremity signatures, but upper extremity error was also detected and tracked accurately with an error compared to a camera-based system about 2.5 seconds. And how accurately can we identify their bit transition times? The entry time error was less than 1 second, exit time error were less than 2 seconds. What's next? Well, one of our future plan is now bring this sensor, instead of asking patient to come to our lab, can we bring our lab and bring these sensors to the patients? For this reason, what we are doing is expanding this study with a mobile contactless observatory. Actually, we recently got a NSF award about $1.4 million of, we're buying a bus and repurposing the bus and putting all contactless sensors all around it along with the camera, and then driving the bus to the patient's home and asking them to and conducting the experiment within the bus itself. What's the advantage? Well, now you can schedule more frequently, and patient doesn't have to travel to our lab. So hopefully it will actually create more data sets and test it out. We can test it out with more patients. Before I stop, I just wanted to mention that this contactless sensor that we are developing in our lab with the advanced signal processing and custom machine learning engines has application beyond stroke rehabilitations in identifying Alzheimer's patients and monitoring Alzheimer-related dementia. Like if a patient, let's say you want to monitor them at home, how well they are, what kind of sedentary behavior they have, how often do they sit in the chair, how often do they sleep, what is their walking patterns. It has an application in Parkinson's disease, monitoring sleep apnea, and then elderly care in long-term facilities. Like even to the point that how often do they frequently visit the bathroom. All this actually indicates some sort of a biomarkers of disease, and we can track them using our contactless sensors without putting any sensor on the patient's body or without using any camera to maintain their privacy and dignity. So with that, let me stop here, and we'll be very happy to take any questions. Thank you, everyone. Go ahead.
Once that you showed, there were some like small fluctuations, and I'm just curious, how much of it is like the noise, and maybe it's better to ask like, what is the signal to noise ratio in this millimeter wave?
So are you mentioning about this particular example that I showed where you asked patient to move lift leg up and down?
No, like generally in class, there were like very small fluctuations.
Oh, the reflection points up, right? That's a very good question. It really depends on how far we want to track the patient. If it's too far, let's say more than 10 meters away, then everything that we're going to get is potentially noise. Of course, we can improve that by transmitting with a higher power. Actually, we are transmitting at a 10,000 times lower power than what's considered harmful for your cell phone transmission. So what is being actually, FCC, Federal Communication Commission, has recommended a certain power threshold beyond which you are not allowed to transmit. And we are transmitting 10,000 times below than that. So to improve the signal to noise ratio, you can potentially transmit with a higher power. But with the experiments that we did, it can track anywhere from 2 to 5 meters away, which is a standard bedroom size environment you can think about. Good question. Any other question? Yes.
I have a question about the sensor itself. So like for the breathing and the heart rate early on in your presentation, is it looking at like the rise and fall of their chest, like the breathing rate, or?
That's precisely what it is.
Okay.
So the heart rate sort of like creates some imperceptible millimeter level changes on your chest area. If you use camera, probably you won't be able to detect. Maybe you want to use a high-speed camera, that might be okay. But the advantage of our contactless sensor is we can actually transmit and get a reflection and sample it at a very high rate, and then pick up that tiny millimeter level changes from someone's chest area. And of course, we want to filter it out. Like if there are correlated movement happening nearby, then the heart rate may get actually corrupted. But as long as the person is like, let's say, in a typical home environment, sitting on a chair, maybe sleeping on a bed, we can pick up their heart rate and breathing rate. But the idea is, yes, heart rate causes a tiny vibration on the skin, and this very act of inhaling and exhaling creates motion in the chest, which can be mapped into the breathing rate. Yes.
Is this approach successful for minor heart strokes also? Because some people will get heart stroke which will not be detectable by the machines.
At this point, it's very hard to answer that question. So it's a kind of like, we did a preliminary study, but that's precisely what we also want to do another study with what we call wake up stroke. Sometimes when patient sleeps, they wake up with minor stroke itself.
Yeah.
And we believe by combination of this measuring heart rate and breathing rate, and also like measuring their limb movement, we can potentially detect that wake up stroke. But of course, that requires a more longitudinal study where you have to recruit and like monitor for 8 hours, assuming that the patient will actually have that wake up stroke. So yeah, but that actually is precisely what we want to look at. But that will be like, at this point, very hard to say whether we can do it or not. But we have some intuition that it might be able to pick up that. Yes.
I have two questions that are kind of related. One of them is that does the voice, the sound in the environment change, affect this data, and if yes, is there any work on like reconstructing voice from that? And other than that, in this case, if someone is listening to music and while they're at home, will this have the same accuracy, or how much?
The answer to the question is yes. If there is a loud music or loud vibration somewhere, our sensor actually can pick up that. And not just our sensor, existing research shows that you can use millimeter wave sensor to reverse engineer's voice, which means that because millimeter wave signal penetrates through drywall, imagine you have a closed room where there's a closed room discussion happening. You don't need an actual microphone inside. You can actually project the signal and actually pick up that voice signal within that conference room itself. And that has been shown in the research.
But you have to do a different processing once you pick up the signal, or?
Yeah, of course. I mean, at the end of the day, you have to look at both the time and frequency domain, right? The thing is, if you, let's say, someone's speaking and you can project that electromagnetic wave towards the mouth, that the vocal cord creates a vibration. And if you can pick up that vibration, you can map it back to the time frequency spectrogram of actual voice, from which you can recover the signal. The processing is, of course, going to be different than this. Now, coming to the point that if someone is playing a music, does it affect? Well, it depends on where the music is getting played. If it is very close to the body, right, we may be able to confuse it with the heart rate. But thing is, we can actually look at the frequency domain, and the heartbeat pattern will be in a different frequency spectrum. Typically, you have a heart rate between, let's say, 30 bits per minute to all the way to 200 bits per minute. Your actual audio signal might be working far beyond that. So you can do a frequency separation too. At the same time, you can also do spatial separation, which means that you can use beams to send the signal towards dedicated direction and sweep the beams very fast to identify and track the users versus track the actual where the music is getting played. Good question. Any other question?
It's fantastic. This class of applications are exceptionally, I mean, very interesting and significant. So, well, this was great overview of the topic that we really need to cover. I hope some of you are interested in, these kind of topics, and consider them for your research options. Right? Thank you very much.
Thanks, Amit. And thanks everyone for listening. All right.